All right, guys, so what we're going to be talking about today is we're going to be talking about something that is known as an initial value problem. Now, an initial value problem, basically what we're going to be doing is taking what we talked about before when it came to antiderivatives and taking that like one step further. So what we're going to be doing is not just finding what the antiderivative is, but we're going to take it one step further, and you'll see what I mean here in just a second. So if I wanted to take the antiderivative of something like 3x squared plus 2x minus 1, and I wanted to find the general antiderivative there, my antiderivative, hopefully you can see that it would be x to the third plus x squared minus x plus c. That would be my antiderivative, like my general one, because I can remember, I put the plus c on the end. That covers every single constant number that this antiderivative could contain, whether it's 1 or 5 or 24601 or 90210. It doesn't matter what it is. That covers all of my different bases. That's what my antiderivative is, okay? Now, as a quick side note, if we have an equal sign, then one thing that is true about any equation is that we must maintain equality. Like if I had x equals 5, what that's saying is x equals 5 and x must always equal 5. If I were to add 2 to both sides, then I could say that x plus 2 is equal to 7, which is still true. My value of x, which is 5, plus 2 must equal 7. It's just a different way to write it. The nice thing about this is this idea that we maintain equality on either side of the equal sign extends to antiderivatives as well. So instead of just saying I have a function and I want to know what the antiderivative is, say I had this. Let's say I said the derivative, dy dx, is equal to 3x squared plus 2x minus 1. If I wanted to know what y equals, if we thought about this for just a second, we could say, you know what? I'm going to take the antiderivative of dy dx. Now again, we just ask ourselves, what did we take the derivative of to get dy dx? And hopefully you remember that that was y. Now, one thing that we should not forget is, and I didn't write it here, it's y, but it's technically plus some sort of constant number. Because it might be y plus c. We don't know whether or not it is, so we have to have that just in case. We just barely talked about the antiderivative of 3x squared plus 2x minus 1 is all of that. So I've got y plus c equals x to the third plus x squared minus x plus c. Now these two c's are not the same, or you can't assume that they're necessarily the same. Okay? So I'm going to call this like c1 and I'm going to call this c2. But because both of those are constant numbers, I could just minus that c over to the other side, or maybe I'm adding it depending on what it is, and I would just have x to the third plus x squared minus x plus, it's a different constant number, but it's still a constant number. So when I have an antiderivative of an equation, although there are technically 2 plus c's, I only have to write one of them. So I've got y equals x to the third plus x squared minus x plus c. And that would be what y is equal to. Okay, so we've got it right there. Now, I know that I've got that plus c, but the problem is that doesn't tell me exactly what an original function was. Like, I don't know what the original function may have been. I just know that I have basically what it is plus this c on the end. So really, the additional piece of information that we would need to know in order to find out what the original function was is we would just need to know how much that function has been shifted up or down. In order to know that, we would just have to find a single point. If we knew a single point that existed on the original function, that would, from that point, we would be able to tell how much the function has been shifted up or down. And really all we're doing is we're solving for the plus c. So we would just replace the plus c in the original function by knowing what the original point was. So if I had this right here, okay, same function. I've got my original one. Whoops, I need to erase that. So I've got this function right here, but notice I have now an additional piece of information. In addition to my derivative, I also have that f of 1, so on the original function, when x is 1, y is 3. Well, step number 1, there are steps to do these problems. Step number 1 every single time is we take the antiderivative. And in this case, we've already done that. Y equals x to the third plus x squared minus x plus c. Step number 2 is we were given the point 1, 3 that exists on the graph. X equals 1, y equals 3. So what I could do is I could put the fact that that is true I could put 1 everywhere I see x, 3 everywhere I see y. And notice when I put in 1 for x and 3 for y, the only thing I have left is c. So 1 plus 1 is 2 minus 1 is 1. So I would have, and then I would minus that 1 over, so I would have that c is equal to 2 in this case. And again, I just found that by substituting in x and y and then solving for c. Step number 3 is we take that c that we just found and we put that back into our initial equation. So I put it back in for c. And what I have done based on the information that I have been given here is I have found what the original function was. I have y equals x to the third plus x squared minus x instead of plus c because of that one piece of information that I had, that f of 1 was equal to 3. I now know how much the graph has been shifted up by. It got shifted up by 2, which is what that plus 2 is. That plus c is what's happening there. Okay? So let's try another one. Okay? Let's follow these steps. Step number 1. Take the derivative, antiderivative. So I get y equals x to the fourth over 4 minus the sine of x plus c, or excuse me, plus the sine of x, because the antiderivative of cosine is positive sine. Then what I do is I take my 3 and my 0 and I plug both of those in for x. 0 to the fourth divided by 4 is 0. Hopefully you remember from the trig unit that the sine of 0 is 0. So I get that c is equal to 3. Now again, we are not looking just to find out what c is. I want to know what the original function was. So the last step on these problems is to take that c, oops, yeah, that's right, and put it back into my equation. Except it's not c, it's supposed to be 3. And that is your final answer. The original function is x to the fourth divided by 4 plus sine of x plus 3. Okay? So if I had one like this, let's say I knew the velocity was 3t squared minus 12t plus 2. That was the equation that defined the velocity for some particle in motion. If I knew the position equation, if I knew from the position equation that s of 1 equals 4, that means at time equals 1, the position is 4, then how could we find the position equation? Well, remember, in order to get velocity, we take the derivative of position. So in this case, if I take the antiderivative of both sides, then I have this right here. Once I have that, I can take my values and plug them in that I have. So I plug in 1 for t and 4 for s. So I've got 4 is equal to 1 minus 6 plus 2 plus c. 1 minus 6 is negative 5 plus 2 is negative 3. So I get negative 3 plus c is equal to 4. So in this case, c is equal to 7. And then, just like I did before, I take that 7 and I plug that back into my original, not my original function, but my antiderivative, where c first appeared. And that tells me what my position equation was based on the fact that s of 1 is equal to 4. Okay? So we can say in general the antiderivative of velocity is always position, and the antiderivative of acceleration is always velocity. Again, an antiderivative is what did we take the derivative of to get where we are right now. So if I had one like this, notice this gives me an acceleration function, then it tells me 2 different things about this same equation. If I wanted to know what the original position was, so let's say I wanted to know, gosh dang it. Nope. If I wanted to know what the original function was, I'm looking for s of t. What we would have to do is we would have to take the antiderivative of my acceleration function. So I would get v of v equals t squared plus c. Then we would have to use the information that we're given about velocity to find out what that constant number is. So I'd have 4 is equal to 1 squared plus c. So c in this case would equal 3. So I would have velocity equals t squared plus 3. Then I would take the antiderivative of my velocity equation to get back to my position equation. That would be t to the third divided by 3 plus 3t plus a different c. This is not the same c we had in velocity. But we're going to solve for that c by using my information from my position equation that I have. So I would have negative 2 is equal to 1 cubed divided by 3 plus 3 times 1 plus c. Okay, so I'd have 1/3 plus 3 is 10/3 plus c is equal to -2. Then I would minus 10/3 from both sides. 10/3, -2 minus 10/3, excuse me, is -16/3. So that's equal to c. So that's my c for my position equation. So my overall answer here would be this, based on the information that I was given and the fact that I started with an acceleration equation. Usually the mistake that people make on a problem like this is they forget that you have to take the antiderivative and solve for c before you take the antiderivative again. Most people remember that acceleration, you'd have to take the antiderivative twice to get back to it. But in order to really solve this equation, you would have to go and find out what both c's are one at a time. So hopefully all of that made sense. If it doesn't, I guess just let me know. Otherwise, good luck.